Okay, so remember we saw the force on a charged particle. If we have a positive charge traveling through a magnetic field, it has a velocity vector and it has a magnetic field vector, and we can calculate that force is QV cross B. We'll see that that'll be relevant in mass spectrometers as we go through this chapter, that we use this idea that a charge moving through a magnetic field will feel a centripetal force. That is a force that's perpendicular to its motion. That is a centripetal force that causes it to move in a circular path. And again, that's the idea behind a mass spectrometer. We'll look at that later. But right now we want to look at not just a charge moving through free space, but a charge moving through a wire, because you really get the same thing when you have a current or charges moving through a wire. You get that the force on that is equal to the current times the length of the wire cross with B. If we look at the units of these two terms, if we look at Q and V together and I and L together, then you'll see that they're the same. So these are really basically the same formulae. We're just seeing that the charge, instead of moving through free space, is constrained to a particular path. So again, the units here are going to be coulomb meters per second, and then over here we get coulombs per second, and then our L is in meters. So they have the same units, and in fact, they're basically describing the same thing: a charge moving along a certain length in a particular amount of time, and a similar thing up here. So you treat these problems exactly the same as we did with the charge moving in free space. You can see this problem again. It's a lot like what we had on the last test, where you just have to calculate that cross product, but that you approach them a little bit differently, and I'll do an example in just a bit. Also want to point out here that our vector quantity is L. Remember, I is a scalar quantity, but our vector is the length L, the length vector. It has both a magnitude and a direction, whatever direction the wire is pointing in. Now, when we're doing the right-hand rule of these things, we'll typically talk about the direction of the current. But remember that the current is constrained by the wire, so it's really the direction that the wire is pointing that is relevant, not the direction of the current, because the current just follows the wire. As with cross products, remember, if I have a cross product, A cross B, the magnitude of that, by definition, is AB sine theta. And so that's the same here. For the force, my magnitude is going to be IL B sine of theta. And if I think about these vectors, I have my I vector here, or excuse me, not my I vector, my L vector, and my B vector. The angle is just the angle between them. So just take the smallest angle between those two vectors, and it'll give you this angle theta right here. We can think of this as charges moving through a wire. So if I have charges that are moving through a wire with a particular speed, I can do my right-hand rule right. I have B in this direction, B is into the page, and so that gives me a force up. Also notice that even though we know that currents are the flow of negative charges, because we deal with this conventional current, we'll always talk about positive charges flowing. Okay, so if I have a force on an individual charge in this wire, then I'm also going to have a force on the actual wire. Again, just exactly like we've been doing before with the free particle, except now our particle is constrained to a wire. Right-hand rule works the same way for these. You can just try these. What are the, remember our equation is F equals ILB, or IL cross B. I let my index finger go in this direction, my middle finger go in this direction, and then my thumb gives the direction of the force. So just try these three rather. A little head start. I'll help you. All right, what's this one? What do y'all think? Yeah, it has to be into the page. So remember, I think that's right. Yeah, I is our L really is in this direction. My magnetic field is up, so it has to be into the page. Remember, be careful here that you recognize that this takes up the x-axis, this takes up the y-axis, so your force is going to have to be orthogonal to both of those, which is going to be along the z-axis. So what do we say it was? Into the page? My force there is into the page. Here, on this one, what is it? It has to be what axis? The x, y, or z axis? It has to be either plus or minus x. What is it? To the right is correct. Yeah. So I, or really L, right? We're talking about I, but really L. B is into the page. And then on this one, let's see, what is this one? This one also to the right? Yeah, it's also to the right. And it's sort of okay on the right-hand rule stuff. I'll hand your test back, but you'll probably want to review this some more for the upcoming test, because you'll see it again on the upcoming test. We're going to skip this quick test. It's not a very good question, but we'll do the next one. You push a 1 meter long piece of copper wire through a magnetic field. Has a magnitude of 2.4 Tesla. You push with a force of 12 newtons. What current is created in the wire? Put in your answer. We'll do about 10 more seconds. I'll stop at 55, 55. Okay, good. A is right, I think. So this is really just applying that right-hand rule, or excuse me, the equation for our force, IL cross B. The magnitude of that force should be ILB sine theta. But here my angle theta, as often is the case, my angle theta is 90 degrees. If it's 0 degrees, by the way, it's just going to go to 0, that you won't have any current at all, because you'll have two vectors that are parallel and you get no current. So here F is 12 newtons, I is what I want to know, L is 1, B is 2.4 Tesla, and so that gives me 12 divided by 2.4 is equal to I. That's equal to 5 amps. 5 times 2.4 is 12. Okay? Let's try this one. This is from an old test. This figure shows a wire, and it lies in a uniform magnetic field. I give the lengths and the angles for theta 1 and theta 2 and the current. I want to know what is the net magnetic force if the magnetic field is 2K Tesla. That means that our magnetic field is coming out of the page like that. And I want to know what is the net force. Now, just to make this simple, we'll just, instead of doing both of these, we'll just do one of these wires. So just imagine that you have this 1.5 meter length of wire in this magnetic field. Current in it is 3 amps, traveling in that direction. What is the net magnetic force on the wire? The magnetic field is 2K Tesla. I'm going to give you a couple minutes, then I'll give you a little hint. You might get caught up on something here. But remember, we're beginning with this F equals IL cross B. What is it that we don't know at all that we need to know? We know B is 2K Tesla. So we know B. What is it that we don't know right off? What's that? We will find it for. What do we need to find it for? Okay, we have the angle, but in this equation, IL cross B, which gives us our force, what do we need to know in order to solve that? What is it? Oh. What is it? Our length is 1.5. That's the magnitude of our length, right? We need to know L and vector notation. Right? So that's your first step. Right? Your first step is to find L and vector notation so that you can do this cross product. I give you the magnitude, the length of L, and I also give you the angle, but you need to figure out what are the I, J, and K components of L. Now your K component of L is what? It's 0. It doesn't have a K component because it's not into or out of the page. But your first step is just to find the X and Y components of L and express L as a vector that's Lxi plus Lyj. So fish back chapter 3 or 4 or whatever, find your X and Y components of L. All right, I'm going to jump in here a little bit. I know that Lx is, gosh, what is Lx? Is it 1.3? What? But how do I find Lx?
1.5 is cosine 30 degrees.
Okay, very good. 1.5 cosine of 30 degrees. And you said that's 1.3? And then Ly is 1.5 sine of 30. What is that value? Do I know?
0.75.
0.75. All right, so then that gives me my vector for Lx and Ly. And now it's just like we've been doing already. So I just say that F is equal to IL cross B. I was it 3 amps? Yeah, 3 amps. Remember, that's a scalar quantity. L is 1.3I plus 0.75J. And then my cross that with my magnetic field, which is 2K. Okay? Now I do that cross product. I get 3 times 2.6 I cross K. Plus 1.5, that's 0.75 times 2, J cross K. Go and wrap that up. Six, 7.8. Gosh, what is I cross K? It's either plus or minus J. Do y'all remember? Is it plus J? I don't remember now. I always have to do my right hand rule. So I is in that direction. K is in that direction. So no, it's minus J. I cross K is minus J. It's minus J. And then J cross K is, looks like that's plus I, right? Yeah. So that's going to be plus I. Plus 1.5 I. All right. I did pretty well on the test for the right-hand rule, for the cross product thing, though a number of you, probably 5 to 8 of you, got your signs mixed up on your I, J, and K vectors. So, yeah, that's a pretty important part. All right, so probably going to see this again on the next test. Okay? You okay with this? Yeah, okay. You're right. Yeah, 3, so this should be 4.5. Thank you. All right. Okay, so big application of this comes about if we have a loop of wire that's in a magnetic field. So let's say that I have this loop of wire. It's allowed to rotate about an axis. Say our axis is right here, and this thing is allowed to rotate. It has a current going through it. First of all, what is the magnetic force on this side A, or on this side? What is the magnetic force on that wire? It's going to be 0, because anytime that my current, or my length, I'm talking about my current and my magnetic field vectors, anytime they're parallel or anti-parallel, that sign is going to be either 0 or 180, and the sign of 0 or 180 is 0. So the magnetic force on side A, because theta equals 0 or 180, this magnetic force is equal to 0 newtons. And then if I want to find the magnetic force on side B, this is going to be F equals I LB times sine of theta. Here my length, if I'm looking at this side, that's going to be I times B, that's the length of that side, times B sine of theta. And my angle theta, in both cases, whether I'm looking at this side or at this side, my angle theta is 90 degrees. So I can just say that this is I times the length B times the magnetic field, by magnetic field B. All right, so that's my force on both sides. They're going to be in different directions. So for example, on the left-hand side, what is the direction of the force? Let's see, my current is down, my magnetic field vector is to the right, like that. And so my force on this side is into the page. My force there is into the page. What about on the opposite side? It's just going to be the opposite, because the current's going in the opposite direction. If you're not sure about that, current is up, magnetic field vector. Did I do that wrong? Oh yeah, I got it mixed up, I'm sorry. So here, force, I is down, magnetic, yeah, this should be out of the page, and then that's into the page. Sorry about that, we'll fix it. Out of the page, into the page. So what I have here is I have these two forces that are pulling on this loop that will actually create a torque on that loop and cause it to spin. All right, so on the left-hand side, it's going to be into the page. Right-hand side, it's going to be, out of the page on the left-hand side, into the page on the right-hand side. All right, so the forces on either side of this are equal in magnitude. because they're both given by this expression, this IBB. If you have multiple, or can I go down from here? We can also calculate what this torque is. If you remember, torque is just F times R. We have two forces that are acting here. We have F1. What is the moment arm, the distance R, for that F1? Now remember, on our torques, if you recall back from last semester, the value for R is the distance from the axis of rotation to where the force is applied. So on our torque loop, what is that distance?
1/2
It's going to be A over 2, 1/2 A. So my F1 times A over 2, that's our first torque. And then I have another torque, F2 times A over 2. These are both going to be in the same direction, right? You have one force on one side that's pulling out, one force on the other side that's pushing in. So they're both either doing counterclockwise or clockwise motion. So they're both going to be in the torques in the same direction. We'll just call them positive here. Put in our values here. We have I dB A over 2, that's just our force, plus IB B over 2, and then this gives us IB AB. Current times the magnetic field times A times B. Because if I add up these two A over 2s, they go to just A. Anyway, we're just sort of getting to a more simplified version for the torque. In general, area is A times B. So we can say then that the torque for any loop is the current times the magnetic field times the area. Now in this idea, we're doing it for a square loop, but it can hold for any type loop, whether it's a square, or pentagon, or circle, or whatever. In fact, usually when you see these things for a circular loop, because circles are easy to make. If you have multiple turns of wire, you just multiply it by the turns of wire. So if you have a lot of turns of wire in your motor or your generator or whatever it is you're building, you get N times I times B times the area. All right, let's try this little quick test on the next page, and then we'll see how this is applied. This wire, negligible resistance. So the only current that is created in the circuit is due to this 5 ohm resistance. That's what it means, that the wire doesn't really have any resistance. Battery and resistor are connected as shown, and the right-hand side of the circuit is inside a magnetic field, 2 Tesla. It says into the page, but it's actually to the right, I'm sorry. Find the magnitude and direction of the net force on this circuit. When you get a magnitude, tell your neighbor what you got. Get a magnitude. Okay, over there. Do you have a magnitude yet for the current? I mean, not for the current, for the force. So your first step is to find the current. When you find the current, our force is just ILV sine theta. So find your current, figure out what is your L, what is your P, and you should be able to find the force. What's the current here? It's 2 amps, right? Ohm's law, I is V over R. So I have 10 volts over 5 ohms. That's 2 amps. All right, and from there it becomes pretty simple. What is, anybody know the magnitude of the force? It's not 40. I appreciate that, but you need to make sure you do your unit conversion because this is 10 centimeters. So what is the 0.4? Yeah, be careful. So whenever I do my unit conversion, I just move it over 2 places to turn it to meters. So 0.1 or 10 centimeters is 0.1 meters. All right, so the current here is 2 amps. My length is 0.1 meters. V was 2 Tesla. And my sine of theta, that's a sine of 90. So that just goes to 1. So it's going to be 0.4 newtons. So there is a force acting on this wire that's 0.4 newtons. On these 2 wires, which are in the magnetic field, what is the force on those 2 wires? 0. And the reason they're 0 is because they're parallel to the magnetic field, so there is no force acting on those at all. So I also want to find the direction of that net force. Our current flows in this direction with conventional current. So I have my current in this direction. I, B is to the right, so it's going to be out of the page. So 0.4 newtons in the K direction, out of the page, is my force. Or you could just write the symbol like that. Okay? You got that okay? There's some homework problems to practice, and you look back at the old test, you'll see some practice as well. You can see types of problems like that. Let's do this clicker question. Here I have a permanent magnet, and there is a loop of wire that's allowed to rotate about this axis. There's a current flowing in this direction. I want to know what direction will this loop initially turn. Will it move clockwise, counterclockwise, or not move at all, or just not enough information? Now remember, magnetic fields run from what pole to what pole? North to south is right. So my magnetic field in this case is running in the plus I direction, or plus X direction. So what is the direction that this loop will turn? Initially, at least. We'll talk about that. The way you'll approach this is just take one side of the loop, say take the left-hand side, and figure out what is the direction of the force on that wire. And then if you want to think about the other side of the loop, you can do so, but recognize that the current is in the opposite direction. So whatever force you have here, you should be able to figure out what is the force on this side without much effort, because the current is switched. Okay, I'll stop at 150. 150. Okay, good. A is right. It's going to turn clockwise. We want to think about the force on this wire. That force is going to be up, right? We have a current that is out of the page. We have a magnetic field that is to the right. This is the left-hand side. Current out of the page, magnetic field is to the right. So the force on this one is up. What about the force on this one, up or down? It's going to be the opposite, right? Because the current is going in the opposite direction. Or really, it's that L is in the opposite direction. But we'll think about the current going in the opposite direction. So that force is down. And now this loop, one will go up, one will go down, and it's going to cause it to turn in a clockwise fashion. Clockwise. Something funny happens when we flip it around. We'll see this next. But what does happen, if you take this loop and you flip it around, then I have, if I flip it by 180 degrees, then I have a current going in this direction and a current going in this direction. So what's going to happen to those forces? They're going to flip. So we'll see that with electric motors, that you have to do something in order to compensate for this, because when this loop goes around, it's then the forces are going to switch directions, so it's going to flip-flop. We'll see how we compensate for that. It's actually pretty clever. Okay. So as the loop rotates, the force changes direction, and when the coil has rotated 180 degrees, the force also changes by 180 degrees. It flips. In electric motors, then, you have to change the direction of the current. After each revolution. So your coil would flip 180 degrees, and then you would change the direction of the current, so that now your forces still keep it going in the same direction, and you don't get this flip-flop back and forth. So there are two ways to change the direction of the current. One, you can use a type of switch. Y'all have used a type of switch in lab to change the direction of the current, where you just, what do y'all call them? Those double pole, double throw switches, those little black switches, where it flips the direction of the current in a circuit. So you can use a switch like that. In a motor, these are called brushes. And they're used in DC motors, in direct current motors. If you've ever rebuilt like an electric motor, you've probably seen these before. Let's see, I have a little video and an animation. Let me show this to you. So in that, they don't have a switch that causes the current to change every direction, every half turn. Instead, what does she do? Instead of causing the current to change direction, what does she do? What does she do to the current every half turn? She does what? No, she doesn't change it. She does what to it? She uses the insulator, and that does what to the current? It turns off the current, right? So every half turn, there are no forces acting on it, because that's why she used the little Sharpie or whatever to insulate the wire on half the side, so that every time it came around to a half turn, it would just turn off the current completely. Here's something that a student does. She actually makes it look really easy. It's very difficult to make these work just right, because the balance has to be just right on them. So this is a similar thing. I can pass it around and look at it, but it just has a little battery pack. And then here's their coil wire. It's not moving right now, but if I turn it on, here's the magnets back here that generate the magnetic field. Let's see. I'm going to set it in. Let me, I'll set it up here so you guys can all see. Alright, so the coil copper wire right here, you can see on this side right here that it's insulated there, and then as you flip it over, it's not insulated here. I'm not sure if y'all can see that, but I'll pass it around in just a second. And then see if I can get it going. Yeah, that's pretty good actually. Alright, so it feels that torque due to the magnetic field and just keeps spinning. So it's a pretty useful thing for electric motors that you can take this circular motion and then attach it to an axle and then cause that or translate that into some usable motion. Alright. I'll pass it around and you can take a look at it if you like. If it stops, no big deal. If it loses balance, it'll stop. All right, the other way, and this is probably the more common way, although for DC motors, that's really all you can do is use those switches to change the direction of the current. The other way to do this is to use alternating current. And this will change direction of the current at some set rate. So like in the United States, for example, our electricity that we get out of the wall changes every 60 times every second. It changes at a frequency of 60 hertz. All right, let's look at a generator. A generator is really just the reverse of a electric motor. So just as a current carrying wire in a magnetic field experiences a force, if you exert a force on a wire in a magnetic field, then a current is created. So if I move this wire through this magnetic field, I have these charges that are moving with a velocity in that direction. My magnetic field is in that direction. So it will cause the charges that are in this wire to move in the upward direction. Remember we talked about conventional current, which is the flow of protons. Hey, Claire? Oh, sorry. He was trying to give you something. All right, so the direction of the current is upwards. And so the generator works very much in the same way as the electric motor, that if I twist this wire in a magnetic field, it will generate a current. Let's see, we'll watch this wind power video and we'll pick up a mass spectrometer next time. So let's watch the wind power. This describes how wind turbines generate electricity. All electricity is made in the same way, that you have a big coil of copper wire, you spin it in some way in a magnetic field, and then that causes a current to flow in the wire. If you have a gas generator, you have a gas motor that spins a big coil of wire. If you have a coal power thing, you have coal that boils water that causes steam to spin these turbines. But always you're taking some motion that's rotating and then translating that into electrical energy.